very good strat lecture that I didn't read the discussion questions on Slack.
Well, we can tell you what they are.
But, yeah, now you can see how I'm going to improvise the answers without much thinking. Sorry. Good. I set myself up very nicely here. Okay, so that's one thing. Like, why did this happen? Well, okay, I'm busy, but I was trying to work out some detail for today's lecture, for this policy optimization stuff, some improvement of what was presented last year. So I was doing that, and so that's like time was passing by really fast. And I forgot to check the Slack channel. Anyways, before that, so two things. One is still, maybe we can talk a little bit about Polytech. And what was going on there, and then we switch gears and we should talk about policy search. Is this big enough font?
Yeah.
Okay.
That's
All right. So regarding Polytech, I just want to make some comments about it. So first of all, it's going to be connected to policy search later on. You will see that Polytech is a very, very close relative to what people like to call natural policy gradients. So that's kind of cool. The other thing is that Polytech is this weird thing that there are two things going on there, right? Like we are changing the policies gradually, improving them. We're not improving them all the way, like in a greedy fashion, like in an SPI, right? And so somehow this buys us this robustness to misspecification. So that was the point of the last lecture. And the one before that, that if you are running, again, a very, very minor modification to this algorithm, which is that you just like estimate the value functions of the policies the same way as in Polytech, like nothing changes there. But you're greedifying, so the next policy is the greedy policy with respect to the value function of estimated value function of the previous policy, then probably, and then there is Tadashi's new proof for that, this lower one that shows that this algorithm is going to be highly sensitive to misspecification errors. Highly means that more sensitive than Polytech. And now we are changing this policy slower. So some people would throw in buzzwords like, oh, we are regularizing, because Tadashi was also telling you that this Polytech algorithm can be viewed as solving this regularized optimization problem where you're summing up all the previous action value functions. You add this entropy regularizer term to that, and you're maximizing with respect to that. So that's like regularized policy improvement. So people are throwing in all kind of buzzwords. So is it really like, what is really going on? This smoothing? Well, there was an old paper that was kind of trying to do the same thing. They called it conservative policy iteration. The idea was that you shouldn't go all the way in improving, in switching to a greedy policy, but you should somehow interpolate, so it's choose a mixture policy between the current policy and the greedy policy, and choose this mixture coefficient in a way that you're not changing the policy too much, because if you're changing the policy too much, there the argument was a little bit wishy-washy, but I think that they wanted to argue that your old data is going to be too irrelevant, and like you don't really know whether you're improving things anymore. So here, if we write Polytech in this way, this argument doesn't really apply. I mean, that is this thing that when you're switching to a new policy, then you're kind of like blindly betting on that the new policy is going to be better in a way, blindly, because it's like it's based on old data, it's based on the previous policies, but policy implementarium actually tells you that that's a valid procedure. But here you have noisy evaluation of these value functions. So it's like, no, you can maybe jump on noise, and so that's not good. So that old paper was arguing, and then they had some kind of theoretical results that was trying to back this up. I think these results now are very clean in terms of like, okay, what is the gain? So the gain seems to be actually robustness to misspecification. That's a very clear win compared to this least squares policy iteration idea. Do we really understand where this gain is coming from? That this regularization, this soft policy improvement, like, oh yeah, by the way, like this is also called soft autocritic sometimes. Like so many names. So okay, let me just finish. So I don't think that anyone really knows. We just stumbled upon that, like, oh yeah, this is possible to do. It seems to work. It does make some sense, but was it kind of derived with the goal of improving robustness to misspecification at the get-go? Like, no, it's like historically, it's like, oh, it was stumbled upon. So we don't have a full understanding of how this goes, and you can expect future papers to, I think, investigate this a little bit further. But
yeah, so when you say improve on the robustness, you're just talking about the fact that we gained, like we don't have a factor of 1 over 1 minus gamma, right?
Yeah, it's factor of age improvement.
And that's necessary for approximate policy iteration from the lower bound, right?
Yeah, exactly. So for least squares policy iteration, we know from the lower bound that it's going to lose an extra factor of age of sensitivity with respect to misspecification errors compared to Polytech.
Right, and then just related to what we updated slightly in the notes before was, so in Polytech we have this like smoothness, and then we also have an average, like we choose based on an average of policies from the past. Right. And then
so both of them are smoothing effects, right?
Right, but then like if we choose like the greedy policy, then it's not still not quite policy iteration or the greedy version. And then I know you were mentioning that we don't really know if both are necessary or one. And like, do we?
That's right.
And is that like? Is there any other knowledge around that? Cause
not much.
Both work.
I think in online learning we know a little that like if you have been on environments, then putting more weight on the more recent reward vectors or loss vectors is not a bad idea. And actually, like there is not much. Like you can start to forget the past. So maybe there is a way to further improve things, and then gradually pushing it all the way so that you are, like the soft autocritic algorithm is actually awaiting the policy and choosing the Boltzmann, I think, like with respect to it. Then you can arrive at that algorithm.
Mm-hmm.
But again, like we don't know whether that's a good algorithm. So now, all right, so there is a clear win in terms of the sensitivity to misspecification, but it seems that the sample complexity got ruined. So in LSPI, what was happening is that the basis of the algorithm is policy iteration, which is converging really fast at the geometric rate, like gamma smaller than 1, then it's like, you know, like you need age iterations. Age is 1 over 1 minus gamma always, right? Roughly age iterations is enough, and then you get like very close to the optimum. So geometric convergence versus in Polytech, if you think about, like there is the policy optimizations, evaluations, the policy optimization part, it's coming from this online learning results, these linear optimization results, and there we are getting a polynomial convergence, right? Like rather than geometric convergence, we are converging only a polynomial array. So because of that, the number of iterations that we need to reach a certain accuracy, even with perfect evaluations, is going to be much larger. In particular, for an accuracy of epsilon, because it's like 1 over square root k convergence, what we have here, you're going to need 1 over epsilon squared iterations. Whereas previously, you had log 1 over epsilon squared iterations. So that's the difference, right? Like, it's like a log factor is missing there. And because of this, the 1 over epsilon squared from here gets multiplied with the 1 over epsilon squared that comes from policy evaluation, right? Like, if you want to get an epsilon accurate estimate of anything and sample average is 1 naught, you need 1 over epsilon squared samples. So in every iteration, and there are 1 over epsilon squared of them, you have to have 1 over epsilon squared rollouts. So altogether, you need 1 over epsilon to the power of 4 samples taken from the simulator. As opposed to previously, we said SPI, it's like log 1 over epsilon times 1 over epsilon squared. So that's like 1 over epsilon squared. So a small logarithmic effect comes from the optimization. So more aggressive optimization, same accuracy in evaluation, lower sample complexity, but sensitivity to misspecification is higher. So that's like this policy iteration did that. And with Polytech, it seems that we're losing on the sample complexity business. So the question is whether this is real or not. Now I just wanted to say, okay, I didn't have time to update the lecture notes, but I think it's gonna go away. So and this is based on an observation that we made in a previous paper at ICMA, just last year ICMA. We had a paper where we kind of point out that Polytech has exactly the right, like if you just change the analysis of Polytech, then you can notice that Polytech doesn't really need to estimate the individual action value functions of the policies. All that it needs to estimate is the average value function of all the previous policies. In a given iteration, you need epsilon accuracy for that. But to get epsilon accuracy for that, like how many samples do you need? Well, it's an average, and for all the past policies, you already have some samples saved, so you can reuse those. And in addition to that, you need just like, if you will have k iterations, one case of the original sample budget. So now what you have is that, okay, k is the number of iterations, it's gonna be 1 over epsilon squared. And you need 1 over epsilon squared divided by k samples for each new policy. And so altogether, multiply with k, you get 1 over epsilon squared. So with a better analysis, with a better understanding, it appears, I hope I'm right. I didn't write up the proof in this context. The proof was written up in a different context, that it works out. I'm pretty sure that it's the same argument. It should work out. That Polytech's sample complexity is going to go down next week, let's say, to 1 over epsilon squared. First, I need to finish phase 1 paper reassignments for ICMA, and then the sample complexity can be improved. Yes?
Is it about reusing information we got about previous policies,
Yeah.
like, or is it just that we have a set of policies and even if we're starting from scratch, we don't need to like compute something for them individually and we can compute something.
What's the difference between the two?
Well, like the second thing I was saying is that okay, if we even if like we didn't have information, even if we don't have information about the previous policies, we have a set of policies, and let's say we don't know about any of them, and instead of we don't know anything about any of them right now, and instead of computing something individually, we can compute something for the average of them. Is this like clear?
I don't quite sense the difference. At the end of the day, though, the algorithm is going to remain the same, the analysis just changes.
Okay. And now, okay, now let's go to the first one. We want to reuse some things from
only assumption, like we are making, I mean, assumption or not, it's not really an assumption. It's like you have the features, and the features allow you to approximate action value functions up to an epsilon accuracy. That's what is being used in the proof or the results, nothing else. And access to the simulator. Right? Yes.
Yep, so, and the average policy would be better than the last policy, is that right?
No, actually the last policy is beating the average policy. That Tadashi's argument with the rewriting.
But if we want to look at the last policy, how would like look at the sample for previous policy be beneficial, like get the same improvement on the bonds you just mentioned?
So you do the analysis the same way as it was shown in the last lecture, where you introduce this mixture or average and you compare to that, and then the next step is to introduce the approximate value functions. And so, like, remember how it was. So we want to show that the last policy is a good one. So first we show that the mixture policy is not a bad one, and then we show that the last policy is actually beating the mixture policy, so the last policy is also a good one. These arguments remain the same. The other part of the argument that was arguing like how well the mixture is approximating the optimum, that argument is changed. All right, so this is Polytech, and so here, kind of what is missing a little bit in the understanding is like what is really that you need to do to get this reduced sensitivity to the misspecification error? Like, is it really the greediness? It's like what is very important here? And I think that being somehow cautious in changing the policies is what is needed. And I think that implicitly this is what Polytech is doing, but it's like almost like stumbled upon, but like you could do this in a more explicit fashion. And then you could have algorithms that are closer to least squares policy iteration and enjoy similar robustness. All right, so that's Polytech. Okay. I think that we talked so much about it that for now we should just forget about it. But like, if you have any questions. Okay, all right, policy search. So this is a very simple thing. That the way so you have an MDP, and maybe it's too big or whatnot. So introduce a subset of all the memoryless policies, and this is a set that you can access through some parameterization, like neural network, describe it, whatever, like something. Boltzmann policies with respect to some state action features. So that's a going example. So some subset of all the policies, and then you just want to find a policy which is the best with respect to, I don't know, like starting the policy from some initial distribution. So so you could have some performance metric like, okay, like what's the average total discounted expected reward for the policy if I started from this distribution mu. And so you want to maximize this. And okay, so so first of all, this is a relaxed objective compared to what we were trying to do. Like previously, the results we had were like, okay, after some computation, I'm going to compute some policy pi hat such that compared to the optimum, there is some lag. Like that depends on the computational budget and the setting and like whatever, right? Like it's suboptimality, but regardless of the initial state distribution. It was like suboptimality universally with respect to all possible initializations. So that's much more demanding. So this seems to be like, okay, we are relaxing this thing, and especially here, what could have been troublesome is that we are using this, I don't know, the compression idea or the feature idea in a very like backwards fashion in a way, in some ways. Although at the beginning I was arguing that it's very natural to start to approximate the value functions, but you could have the features, then like, why don't you go directly for the policies? Like eventually you want to have policies. The value functions were a vehicle to get you there. Like, why do you care about approximating value functions? It's backwards, right? Like, we are using a tool to achieve your goal, but like, why don't you go directly for the goal, right? So it's what's nice about it is that it's direct, right? And this value function approximation was highly indirect. Okay, now this font is too small, I guess. But okay, I will try to enlarge the font. Can you still see it?
Yeah, I think it's okay still.
It's okay? All
I
right.
can cover this board with my laptop if you want.
Huh?
I can cover this board with my laptop.
I mean, it's if people say it's okay, then it's okay.
No complaints.
I will write. Like I don't need to write a lot. Okay, so so what goes for this is that it's more direct, right? So then why would you start with an indirect way of solving a problem when you can go for the direct way? And so that's, I think, the rationale for trying to do this. And then the question is, okay, how can we perform this search? When can we perform this search in an efficient and effective manner in the space of policies? And so these are the questions that come up as usual. Right? And so today there is only one result to be covered, which is a negative result, which says that this is highly dubious. If you set out for designing a universal procedure that works no matter what parameterization, then this procedure is going to be inefficient, very likely to be inefficient for some problems for which you might otherwise be able to design solutions or not, like maybe not. Actually, the story is somehow that, I don't know. Let's talk about the story later. But you have seen also the lecture notes. So the theorem is the following. So the problem of finding these argmax, maximizing over a policy class, is NP hard. And now, okay, like this seems a little bit bogus, like what are these things, what is being scared? So we need to come up with some MDPs. So the size of the state space is the scaling parameter. We're going to have, in these MDPs, we are going to have the same number of states and actions. So that's the scaling parameter. So the NP hardness will be asking polynomial time computation as the size of the state space, which we happily had for tabular MDPs. Calculating the optimal policy didn't take us much time. Policy iteration, beautiful results. You can get exactly the optimal policy. And so what's the policy class? So the policy class is going to be super simple. It is just the distributions over the action space. So these are the blind policies. So these are policies that don't care about the state. Just use the same distribution regardless of what the state is. It is just like, forget about the state. So in a way, okay, so this is a small policy class. It's basically the simplex over n. Right? So we are searching on the simplex, trying to maximize the value over the simplex, and solve this maximization problem. And this is NP hard, and the proof goes by reduction to maximum independence set problem. Specifically, if you can solve this maximization problem, then for every n, we are going to embed a graph into an MDP. We're going to represent the independent set search problem as a maximization problem for maximizing the value of a blind policy, such that if you find the maximum, then you can read out the independence number for that graph. And it's known that finding out the independence number of a graph is an NP-hard problem. It's a decision problem. Is the independence number larger than this and that? And this happens even for 3 regular graphs. So these 3 regular graphs are the graphs where every vertex has 3 neighbors on it. Exactly 3 neighbors. There's 3 regular. And the reduction is based on a very beautiful odd result from 65, which rewrites finding the maximum independent set, the size of that set, this independence number, as the solution of a quadratic optimization problem over the simplex. And that's how the whole thing is connected to MDPs and optimization over the simplex. So once you know that odd result, you look at it and you say, oh yeah, okay. Over the simplex, some quadratic optimization problems are hard. Can we embed those quadratic optimization problems into MDPs? Look, can we kind of use the MDP machinery to express these optimization problems without incurring much overhead in the conversions between them? And lo and behold, you can. So this is what's happening. And so what I spent time on, and why I was not reading questions and the discussion, is because I found this result a little bit brittle. Because it just says that finding the exact maximum is NP hard. Okay, so that's to be contrasted with finding the optimum policy without restrictions on a policy. We know that can be done for this is for discounted problem. So for a fixed discount factor that can be run in strongly polynomial time in the size of the MDP. So now, the only thing that you change is that if you restrict the policy class, how ironic that over a smaller set you have a harder problem. But it's somehow understandable. Like in a smaller set, it's like you don't have that much space to move around. The problem became very hard. So this is what's going on. So the cautionary tale here, I think, is that since policy search is asking for finding policies in a compressed set of policies, that's the essence of it. What might be happening is that this compression introduces bottlenecks and computational challenges that are insurmountable. Like no one will be able to overcome this. So that should be the cautionary tale. Yet, you look at this and then you say that, well, who cares about finding the optimum? How about just finding an epsilon optimum, right? So can we find an epsilon optima policy? Maybe we can find epsilon optima policies, and this construction just like is blown out of the water. Like it's so that's the question. So does hardness apply for the problem of, okay, not argmax, but find policy pi in this set such that G of pi is at least this large. So here you have the same pi that's important, minus epsilon. And epsilon is fixed. It's like 1 or like 1/2, or maybe if epsilon goes to 0, then you expect that the computation complexity can blow up, like 1 over epsilon, I don't know, some power. That should be fine if it's polynomial. Go ahead.
Yeah, just something about the previous one. If we assume that this restricted class contains the optimal policy, could we still come up with these examples?
No. Because then, if you have a finite MDP, you just compute the optimal policy, and if someone guaranteed that this pi set for every choice is containing the optimal policy, you ignore pi. You do the computation, good old-fashioned policy iteration gives you optimal policy in polynomial time. You return it, it's in the class. If there are multiple optimal policies, maybe not all of them are in the class, then maybe you have to kind of do some massaging of after you find a solution. I'm not sure that this is, yeah, I haven't thought about that part, but if you guarantee that any optimal policy of the MDP is in the policy class, then of course just run policy iteration. There is no problem, unless you were expecting that this is a good class because it only has, in this case it's not a big compression and parameters. So how many parameters does a policy have? It's not much more, because for here you need to specify an action. Deterministic policies suffice for each of the states. There are n actions, n states. So how many? How big is the table that describes the policy? It's not too big, n log n or something. And so this has the size of n, right? Because for every action you have. Okay, so it's there are real numbers here, but fine.
I just have a follow-up question. If we want to use policy iteration to find the optimal policies, maybe we want to find a lot of them, maybe all of them. What is that complexity? Or
oh my gosh, I think that people have actually looked at how to find all the optimum solutions, starting with graph search problems. I do remember papers vaguely. It's modifying the basic algorithms to keep track of all possible solutions. I don't know. I was never too interested in this question.
So I guess that would be tricking the tie breaking in policy iteration.
I mean, thinking a little bit more, this is not too hard. If you just run policy iteration the way it is, it finds you not only the optimal, an optimal policy, but it finds the optimal value function, from which I think that's the fundamental theorem tells us that all memoryless policies that are optimal are greedy with respect to the optimal value function. So you can, knowing the optimal value function allows you to solve this, let's find all the optimum policies problem.
Yeah, I guess.
So that's not much harder. I think I do remember when I don't know, there were some papers where people were trying to track these things, but maybe they were not using dynamic programming, and that's why it was complicated for them. But graph search problems where I don't know. Anyways, where were we? Okay, so does the hardness apply for this problem? And so I was looking into this, and there are several difficulties of just like trying to apply what we had in the lecture notes. One of the things is that if you think about it, like it's reasonable, maybe this is a good start, what we had, this reduction, quadratic optimization over the simplex, with this embedding of independent set problem. What you would need to be able to say is that if I can find an approximately optimal policy, what does it mean? Like I can find then an approximate maximizer for this quadratic optimization problem over the simplex, then that would entail that I can find an independent set which is not necessarily an optimum, but a good one, right? So, but no, you have to do some rounding or something like that, right? Because we were searching over the simplex. So that the idea is that like the solutions, if you're setting up things well, that the solutions to the quadratic optimization problem are going to be integer valued actually. You're optimizing over the simplex, but you're actually going to select one of the actions. So it's going to be just like the policy that you find at the end, it was set up in such a way. The true optimum is just selecting all the actions all the time, and that's all fine. But once you move into the realm of these approximately optimal solutions, that's not the case anymore. You can find probabilities, like you find a probability distribution. No, okay, how do we relate this to the independent set problem? So the other part of the other side of this question is that, okay, the plan would be that if things are going well, then from an approximately optimal policy, you can read out an approximately, like a near optimal independent set for the graph. Just a second.
Yeah,
Okay.
if I remember correctly, you said that this is an NP-hard problem with no approximate solution. So doesn't it implies if you find an approximate?
Yeah. So in the notes, I was saying a bunch of things, but it was also saying open problems, and if you read it very carefully, it's kind of like, I didn't know the answer. I still don't know the answer. So yeah, and I'm coming to the approximation part. So the plan would be, okay, find the reduction such that the reduction allows you to do these things. Like you find an optimal policy, then that implies that you find an approximate optimal solution to the maximum independent set problem up to a certain approximation factor, and then use a result that says that that's hard. And there we know, actually, I asked Zach, he's our local expert on complexity theory, and he told me that, yeah, it's a fascinating topic, probably the most studied topic in computational complexity theory, this independent set problem and its relatives, and the result, that is the current best result, is that getting anything better than 94 over 95 approximation to the maximum independent set problem is NP-hard. So there is this magic threshold. You cannot go beyond the magic threshold. Then NP-hardness kicks in. So you could try to use that, and that result, okay, sorry, the 95 over 94 comes in because we're just talking about three regular graphs there, which is really helpful because this whole reduction was based on using three regular graphs. So this is the part that I didn't quite know when I was writing. So now I know this, thanks to Zach. It was easy, just ask him. And you might be able to hope that like you can turn things around, and then this gives you a hardness result here as well. But I'm not quite there. Okay, so the next difficulty is that like it is known that the quadratic optimization problem that I was using in the reduction, that is based on this older paper, is actually pretty unstable. So it's like it can have spurious maxima and whatnot. So it doesn't satisfy properties like if you find a local maximizer for that objective, then that's a maximal independent set where the objective value would directly translate to how good that, like how big is that maximum independent set. You can find solutions which are nothing to do with maximum independent sets. So that reduction stops there, but no, I found a paper which fixes that reduction. There in that reduction we had once in the diagonal, you change it to 1/2, magically the problems go away. That's a paper of someone else back in the day. And so I hope that you can put this together and then eventually you can get this hardness result. So I conjecture that that this hardness result is going to apply. With one more caveat. The caveats never stop. To get this hardness result, even with the argument that is presented in the lecture notes, the hardness result is kind of like presented in a weird way. If you want to get this hardness result for a fixed epsilon, you would need to scale gamma towards 1 with n. So as n gets large, you are forced to choose a horizon which is scaling with n. Actually, the horizon has to be like 195. And that's enough. So that's based on the current reduction. And so that result would say that, okay, so the conjecture would be, yes, NP hard if gamma is dependent on n, and it's done, it's chosen in such a way that it's like, this is larger than, I don't know, 95n. It kind of makes sense, right? Because what are you going to use this n for? Like, you're creating space, increasing the size of the problem, the graph. If your discount factor stays constant, then it's like, I don't know, like, then you are only carving out a small part of that graph, right? Like, maybe you're not able to access everything there, and like, it's like, but I'm not sure. Like, maybe a stronger result could also be proven that would say that for any fixed gamma close enough to 1, let's say, this hardness result holds. I don't know that. Like, the tools that I know about doesn't give this result. So that's an even stronger conjecture. But the status of that is somewhat dubious. I don't know. But most likely it's true. It is hard to imagine a world where just because your planning horizon is not increased, this problem doesn't get hard. This approximate problem doesn't get hard. All right, so one more caveat. So this goes into like how to read a result which is very, very short. It's like, we have this result and we can talk about it for 2 hours. So if you look carefully at this result, you will see that the optimal value scales with the horizon. It's like h. Like around h, 1/1 minus gamma, there is a little room for when you're choosing the policy, then it's like it can, deviate from this h, go down a little bit, but not too much. You can very easily find solutions. I think that like within h minus 2n or something, 2/n. It's like, it's very, very close. So that's for a fixed gamma. But like, if I start to scale gamma, then like I can make some term really big. So then I can set an n, and then, okay. Then even in that case, I think that the room that you can play, that you have for playing is not too big. So long story short, when you have these like really high values, and you're demanding a small absolute error. It's sort of weird, and this value is being scaled up. Like, a more relaxed version of the problem would be not to find a policy which is this close to the maximum. Let's call this guy J star, but it would be this problem: find pi. Okay, write it this C stars. For some C between zero. It's like at least half of the revenue is made, right? So is this problem high? I have not the feeling. Probably not. I have the feeling that whenever this compression happens, you can create a hard computational situation that uses this compression in uncanny way. All right, I stop here. I have nothing much else to add. I think that in this lecture there was nothing much else. Only these results, and maybe something at the end about that okay, so finding a local maximum could be a way out, right? So maybe you can quickly find a local maximum. We could be happy with a local maximum. That seems to be a step back compared to something like this. By the way, so here I'm writing this V star, but you should also recall that this doesn't have to be V star. So for example, in the tensor plan result, we take any policy whose value function can be expressed with the linear combination of the features. And we take amongst those policies, we take the best and compete with that. So that there is some, like very strong improvement on, because here you could say that, once you introduce these features or whatnot, this compression, then why do you even shoot for the optimum? It's like you should be shooting for just like this, like the restricted optimum, and somehow TensorPlan is doing that. That's what I'm saying. So with value function approximation, you can do something like that. So here it's a little bit unclear, and yeah. So in the literature, you can sometimes hear people saying or can read people arguing that policy search, because it's a direct method, it avoids all these problems with value function approximation. It's great because of this. And I think that it's a very, very interesting position. I'm not sure whether it's true, but this is like what these classes are about, right? Like we are trying to find out. But it's really true that if you're switching to direct policy search, you could be gaining something. My personal opinion is that it doesn't seem so, and if you're honestly, but I should be free to change my opinion at any point, right? But like based on what I have seen, and this is more like anecdotes, but like I've been around, and then, like looking at the algorithms that actually deliver some performance, they all estimate value functions. Like they might be sold to you as policy search, but most of the time they end up with using value function approximations here and there, and then like who tells the difference between these algorithms, right? And then the differences are kind of like washed away. And intuitively, like this value function approximation is maybe not such a bad thing. I don't know. I don't want to defend it or argue for it. I'm actually very curious about finding other ways than using value function approximation. It's just that like it's not trivial. It seems that there are some forces here that they don't want this to happen too often. Yeah.
So actually predicting that those kind of like both of them, how would you classify it?
Yeah, I think we should all resist all these classification questions all the time. I think that is my short answer. It's not worthwhile. I guess, okay, so I've been thinking about this, like why do people insist on, model-based, model-free, actor-critic, policy gradient, like which class of methods your method belongs in, like belong to this camp, that camp. So to some degree it's useful as a way of quickly communicating what your algorithm is doing. If the other person is speaking that language, then you can tell them, oh yeah, like you take the policy gradient and you do this and that. That's fine. But I don't think that it has any further significance. To me, the significant questions are this, like, can you do it? Can you do it efficiently, effectively? When can you do it? These are and then I don't care about what is the method. I care about what problem it's solving, for sure.
I feel like it's nice though when you like classify the methods at least in some strict way, because then you see for what methods what results you can get and for what other methods you don't get good results, right? Then you can see that like.
But these are often lies, I find. These are often based on simplifications, overlooking, and I find that like if I push myself, then I can usually interpolate between any classes of methods in a continuous fashion, and then I can cross these boundaries, and then like this falls apart, right? So it's like, yeah, I'm with you. Like it would be a nice thing, and I really want to say that regularized methods are advantages because of this and that. It turns out to be half-truths. That property that people are shooting for, yeah, you can achieve it with other ways. So it's like, and is that the only thing, only benefit of that approach? Well, sometimes yes, sometimes no. I don't know. It's like these are half-truths that people are saying, and it's I don't know. There is I can see that there is some value in trying to create a black and white, nice, clean picture. It is just that I'm not sure whether that picture really does exist.
Right, but like I feel like just stepping back, kind of in all the results we show, don't we kind of state some like sort of like binary black and white assumptions, like okay, maybe we want algorithms that operate under Q star reliability or something, and then we say how they perform, and then Q pi reliability, and then here it's like, okay, we want algorithms that don't store value functions, and then other algorithms that are allowed to store value functions.
Oh, like this part.
Yeah, this
don't
is
store this and that.
Like,
I think it's really hard to enforce. So we never did that.
Right, well we don't enforce it, we just like say that under these, well I guess we do kind of enforce it, right? We say like, these are the assumptions we work under, and these are the
Not
results
like what you store in memory. We never made any assumptions.
Alright, yeah, we
like
don't
that.
make assumptions, but I was just saying this is like a similar kind of thing if you do make those assumptions.
No. And actually I would push back on that. These are assumptions. If you're doing all this well, they cease to be assumptions, but they are more like peeling away the big class of MDPs. So, to tell you an example, QPy reliability. It's not, you shouldn't say it this way. You should say that, well, okay, so there is this constant that tells me how well I can approximate all the QPy functions with my function class. And this constant is going to show up in my, so it's applicable to any of the MDPs. Maybe the bound is vacuous, and then maybe there you can draw a line and you can say that, okay, like clearly if this approximation constant is bigger than something, then all these bounds are vacuous. So, but it's yeah, I think there is a benefit of not thinking that way, like black and white. It's not really, these algorithms can be run no matter what. So that's the other thing, right? Like if it was really true that these algorithms heavily rely on these assumptions, I mean, then you would probably first look whether the assumptions are satisfied before you try to run them. No one does that. Just run it.
Right, but we only have guarantees for those assumptions.
No, there are no assumptions. It's like it says for any MDP, blah blah blah. I mean, like there are assumptions because it's an MDP, is the access protocol. Those are assumptions because that is really needed by the algorithm. The rest is just, yeah, it works no matter what. I'm like, if you do it right.
Right, we can run them, but I guess we don't have any guarantee of how they'll perform.
They do. These are the misspecification errors.
Oh, right, yeah, like if we know the misspecification, then
we don't need, a lot of times the algorithms don't need to know the misspecification error. We have to be sensitive to that, whether they need that as an input or not.
Sure.
Sometimes they do, then it's a problem.
Right. Yeah, it'll still run. There's some result. It's just that if someone were to come and ask you, like, how are you going to perform in this environment, you can't tell them unless you know the misspecification error of that environment to give them a bound on the worst case performance. But maybe that's not important because you'll still perform
almost as well as anyone else.
Yeah.
So maybe you have a lower bound that says that under these circumstances no one can do better. Then you say that, okay, we're just doing as well as we can. But of course, okay, so the way, the thing that is in my head when I'm thinking about this is that here's the class of MDPs. And then what happens when you choose a method is that you're kind of like slicing it up into these small slices. And it's like, this is your, I don't know, misspecification error. So you create an axis of misspecification error. And so here are the problems with very small misspecification error. Here are the problems with big misspecification error. And now, okay, your method is creating this ordering across these problems. These problems, it's going to work awesomely. These problems, it's going to work really poorly for. And you prove that, okay, like if someone accepts this axis, then no other method can do better. Then, okay, we can talk about whether we want to choose another axis. And this is like choosing something like this rather than what we were doing before. That's what it's saying. And then we can ask, okay, how many axes do you want? Can you combine them? All these are valid questions. I think these are only questions, actually. Like all these other questions about, like whether this method is this class or that class, I don't know.
Yeah,
like
but I'm just saying
that
like,
useful.
if you take each of these as like a new axis of values that you can sweep over and define, like you break up each one of these new dimensions we introduce kind of like breaks up the problem into subclasses of MDPs that were
Well, you can
they're like each
I don't know,
parameter.
discretize this axis and then
or it can be continuous, it doesn't matter. But
right.
I was just saying that for the solution, well, like with the policy gradient or or policy search or value point, you can also kind of think of it as like another axis of like, but I don't know if that's a meaningful one to break things up into.
Well, we would want to know that, right?
Right, so
it would be meaningful if we can create efficient, effective algorithms that are behaving nicely along this axis. Right, so that's exactly the question that we have. And here we do have some doubt that like at the get-go, whether this is going to work, right? So that is kind of like, that stops me a little bit.
So now I'm confused, going back to the original question. I was saying that it seems like it would be meaningful to classify algorithms or like say that, okay, I restrict you to only represent, like only search over policies and you can't store value functions. that seems meaningful in the sense that then we can get results like this over those, like, then you shouldn't be using those type of methods, or you should, or something like that.
Yeah, so we really need to talk about this. Don't approximate whatever, like
Yeah.
I just put value functions here.
Yeah.
Or don't approximate the model, or whatever, right? Like, I want the model free, that means that I'm not going to store a model.
Yeah.
Yeah. I don't know how to really give meaning to these questions. I wish I knew. I think that these are questions that we make up because we think in terms of these concepts. But to the computer, that is the memory. It uses the memory for something, and then like whatever happens, happens. When we are trying to prove a lower bound against some class of methods, it's really hard to say that the method shouldn't be using a model. What does it mean? Okay, if I create a black box that is nicely separated from my algorithm, that has the interface, and I call this a method, then it's not allowed to use the interface, it's fine.
Mm-hmm.
So if you can somehow break up your things into these spots and like compartmentalize, maybe you can do something, but generally we're not able to do this. So as a theoretician, I really do not know how to answer any question of like, what are the limits of model-based methods? What are the limits of model-free methods? And then this classification seems to be falling apart on me, at least because I can't do much with it. Like, but it's not. It doesn't necessarily mean that no one can do, or it will never happen. Maybe someone will come along and then create some class of algorithms for which everyone accepts that, okay, this characterizes what we mean by model-based algorithms.
But like just for the model-based, even like, don't we kind of like for planning? Isn't the assumption that we have a simulator or a model,
Yeah.
and then when we go to online, we already have the assumption that there's no model? And
We don't have the, I mean, like, the algorithm can build a model if it wants to, right? Like,
Sure. Oh yeah. I guess.
yeah.
So-
I think that this, okay, by the way, there was a paper, there are some papers, I think Oleg Harvard is maybe on a paper with some other Microsoft guys who are talking about the limitations of model-based reinforcement learning, and they try to formalize it.
Mm.
Don't really like that, but the way it's done, but
Yeah.
these are good questions.
Yeah, I guess another interesting, because yesterday in Rich's class, I think some of us were in Rich's course, he like spent a lot of time writing out this agent who has specifically a box for the model, a box for the value function, a box for the policy, and it's kind of interesting because you were just talking about like compartmentalizing into these different chunks.
I mean,
And then he believes
from the
that they're like-
perspective of being constructive and designing algorithms, it kind of makes sense. I mean, you rather want to start though with a problem, and then if the problem dictates that you should have these boxes, choose these boxes. But very often these boxes do appear in these algorithms, right? I mean, we haven't specifically talked about any model-based solution method, because I think that if you have a simulator, it's kind of ridiculous to try to build a model from the simulator, although people do this, because you could say that, okay, the simulator has all this infinite amount of knowledge, and then you kind of extract it, and then no, you have it, and you can do computation in this alternate form with this compacted knowledge, and maybe that's helpful. But in online learning, it definitely does come up, or batch learning. It's like it seems more reasonable to try to do something like that. All right.
Okay, yeah. Maybe I have some other questions, but we can talk offline, I think. We should probably move on to the
Slack
questions.
Yeah.
I guess, do the people want to ask?
Sure.
Yeah, you
I
got
have-
more upvotes.
I have basically three questions. One is that in the lecture notes you said something about state aggregation. So the policy, the hardness result holds even for state aggregation. But how does state aggregation affect hardness? And if we do state aggregation in some way, would it make the problem simpler? I guess not, but.
I guess if you do state aggregation in a way that you're not doing state aggregation, then the problem remains easy. If you allow any form of arbitrary state aggregation, a special case of that is to aggregate all the states into one big state, and this is what was happening here. Then we see these hardness results popping up. Clearly, if you allow, I don't know, to compress an arbitrary number of states, then, but you don't allow me to just have one aggregated state, but I need to have two at least. I can, save one state for the original one, and all the n minus ones are aggregated. It's the same hardness. So for a lot of these problems, I think we're gonna see hardness. It's hard to avoid it. If you want some sort of generality, it seems that the extreme compression is when you don't have states and you still want to know how to act, and that seems to be just fundamentally hard.
And I guess so. Another question was, you said that in the notes there was something related that we chose the linear Boltzmann policy class usually, and you said something along the lines that we want our policy search methods to be agnostic of the parameterization policy. But are there methods to choose good parameterizations of policies without being agnostic?
Okay, so I would understand the question without being agnostic. So that made the question too complicated for me. So what does it mean that?
Basically, my question is, are there good ways of parameterizing the policies depending on the problem, or do we?
So this result is independent of policy parameterization.
Yeah.
So that kind of tells us that it's kind of, this is just challenging a bit. Once your policy parameterization is able to support something like this, it doesn't matter what the details of the parameterization are. The search is not going. This is computation complexity hardness, right? Regardless of how you're organizing things, including how you're representing things. You can try to represent things by exponentiating or sinusoidals or whatnot. It's not going to change the basic fact that it's hard.
I think you also said something like this problem could be harder than NP-hard.
Yeah. But okay, so I'm not really an expert on computation and complexity, so I don't even want to go there because I wouldn't really understand what I'm saying.
And
so I'm a student there.
I guess my last question is more kind of vague, but you said that when we compress the value functions, those methods kind of worked well, all right. But when we're compressing policies here, it seems that the problem becomes really hard. So is there any deeper reason why compression works for value functions? I guess you talked a little bit about it, but are there any other reasons?
Yeah, I don't know. Yeah, it's I don't know the answer to that. I think I want to know too. Yeah. I guess maybe the lesson is that, okay, dynamic programming was the tool to solve MVPs in the first place. So if you try to move away from dynamic programming, you're going to lose dynamic programming, and that was the only tool that you could use to solve this problem. So it's like, what did you expect? Okay, so the funniest thing is that with Polytech and all of these things, they don't look like it's dynamic programming, but they are dynamic programming. Anything that uses value functions is dynamic programming. That's the core idea in like dynamic programming is about introduce value functions to compress stuff. And so, yeah.
Here we're not like losing dynamic programming. This is like saying, so like in this hardness result, I mean, the algorithm could still have value functions in it, but it still wouldn't help.
Yeah, it could try to do something with value functions, but yeah, the problem is changed in such a way that the value function approximation is not a first-class citizen. It would be a second-class citizen in the sense that it's not part of the problem definition. It came as a solution technique, which would be awesome. I really want that. But it seems that we are not having any success with it. Yeah.
Just one question. Why do we care about this ultimate state aggregation case where we aggregate all of these states in one state?
So that's kind of the same question as what you were asking. If you didn't aggregate all the states, I can aggregate almost all the states. We are at the same page. Hardness still applies. So if we care about universally solving the policy search problem, a special case of that is this. If someone wants to have an algorithm to solve this, then like they're going to face this challenge at one point, like it's somehow embedded into this bigger problem. And so now the question is, okay, can we somehow create situations where the hardness doesn't apply anymore without actually doing this? Because we can avoid the hardness with value function approximation. Sometimes, like sometimes we saw the lower bounds. Sometimes you can't. But sometimes you can, like the Polytech case, like that's a really nice case, everything is under control. But of course, we are more ambitious. We want to go beyond that. But they just ask us that like, okay, like there is going to be some limit. You can't just like erase all of this. You will need something. Make sense?
Yeah. Yeah. But maybe there is a policy who doesn't need to aggregate all of the states in one state. So why it also has to face this challenge? Like, I mean, like, why we assume that all of the methods has a case in some MDPs that have to aggregate all of the states into one state.
So maybe what you're asking is that like, okay, maybe we can just like, here are all these problems that we can talk about. This is not the MDP, but policy search problems now. Why don't we just forget about this hard part? Yeah, like, sure. But like, which part remains? We don't really know. This just says that there will be a hard corner. It doesn't say that this is the only hard corner, by the way. It's like, there could be many other hard corners. It's just like pointed out that, oh, look, if you're not careful, then you can run into trouble. So now the next question is, okay, can we somehow remove some part of this hardness, restrict somehow the problem, without falling back to value function approximation? So that is really the question. Yeah, so it's, I guess like we are talking about the same thing. Like, I was asking the same. It's like, yeah, we clearly, this could be a corner case that you can avoid maybe, somehow. But then you have to name it, like how are you going to avoid this? What is the assumption that rules out this, that this is happening or something similar?
the hardness result for approximate policy search, and this I was a little bit confused about the how and epsilon should be chosen, like which of them come first.
Okay.
And
For the approximate hardness result?
yeah, and
Yeah.
I think after this class, I think it is that if you want a fixed epsilon for the, like let's say the solution method can solve for a fixed epsilon, then you want to try to attack the policy search, approximate policy search, then you find a lot of MDPs with size n, and then
As n grows.
yeah, as n grows, the problem becomes NP hard, and then you try to do that. You try to prove if you can find that epsilon optimal. That in that sense, epsilon optimal policy is equivalent to finding a fixed independence set size, a fixed size of a fixed proportion of the independent maximum independent
That's
set.
right. Yeah.
Okay. So now if
And so what I was telling you that I can do that, I think, with this
by
choice.
choosing gamma.
Yeah, which was not what was in the notes.
Yeah. In
The
the
notes was not doing
chose
that, and so
epsilon, yeah.
it was like, last year I didn't know what I was doing.
So also this new thing is that the NP hardness only appears when this proportion is higher than like 94, 95.
Uh-huh.
Okay. Because in electron is like 50%.
Yeah, so I think that it was better to talk to Zach about this. It cleared up a lot in my mind. I was trying to read about it in the books and like internet, and it's like, okay, big lesson for everyone here. Just talk to someone who knows the thing. It saves you a lot of time. The internet is great, and the books are great too, but it's not the same as someone telling you directly that this is the result to look at.
Okay. Then is also an interesting question that it is an open problem. So there's also hope in that if you just want to find an epsilon optimal in that sense.
Right. So all of these are conjectures now. Actually, if you want to work on this, let me know. I'm happy to share what I have. I'm too lazy to finish these things, so it's I wish I was just too lazy.
But I think it is clear in the class now.
Yeah. Okay, good.
Thanks.
Yeah. All right. Any other questions? People on the call. Hey. How are you doing?
I'm great.
No questions? All right. We want to include you, you know. You can't be here, but you can still, I don't know, ding ding. All right, good. And this was the class for today.